Hello everyone, my name is Pan He and I'm from ECE department. This presentation is for pattern recognition course, and my title is Feature Learning for Deep Face Recognition. To begin with, I'll briefly introduce three main stages exist in face recognition system. The first stage is face detection. It will localize all the faces within the image. The second stage is face alignment. It will identify geometric structure of human faces in images such as eyes, nose, and mouth. The last stage is face recognition. So basically, it will identify or verify a person by comparing and analysis patterns based on the person's facial contours. In our project, we can take the face detection and face alignment as the pre-processing part for the face recognition system. So in this project, we are more focused on the face recognition part. These are some images to illustrate these three stages. As you see in the first stage, in the first pictures, for face detection system, we always have some bounding box for the person's faces. For the face alignment, the white pixel, it is some features for certain part. Like in here, there are how many line features for the nose. And the last pictures, given input facial images, the system will tell us the identity for that image. Usually, when we talk about the face recognition model, we have two approaches. One is called face verification, and another is called face identification. So the face verification involves a one-to-one check that compares an input with only the image that the user claims to be. In simple words, if you stand in front of a face verification system and claims to be a certain user, the system will only check if you are that person, that user or not. A face identification is another thing. Like it involves one-to-many comparison of the input image with template library. For example, in a face identification system, the input image will be compared with all the classes, and then a decision will be made so as to identify to whom the input image belongs to, or if it does not belong to the dataset at all. So to begin with the image classification recognition model, we want to show some motivation for successful recognition system. So in the traditional machine learning algorithm, we know that when you do the clustering, you want the right pictures. Like for the intra-cluster, samples belongs to the same class. You want their distance as smaller as possible. And for different classes, or for the inter-cluster, you want the distance as large as possible, so that you can draw some clear boundary for different clustering. And it also applies in deep learning method. As studied before, the deep learning feature, the feature of the deep learning model is only separable. That means it can make some boundary, but not so clear, because different classes, the feature of different classes have some overlap. So it's only separable. But we want some more descriptive features, as in here, like as well, the margin here. So we want some discriminative features. That's the key factor to a successful image recognition system. That's why center loss being proposed in recently. The center loss will learn some discriminative features with more interclass dispersion and intraclass compactness. It acts as a L2 norm-like recognition term to minimize distance between features and their corresponding center features. And when we apply center loss, we usually have a joint training version. That is to say, we have a softmax plus center loss. The softmax loss will focus on enlarging the interclass distance, and the center class will make sure that the distance between the feature and its corresponding center features as small as possible. Based on this equation, I've already implemented some center loss framework for these algorithms, and I also made some pull requests to the PyTorch, a popular deep learning framework. So you can find my implementation on these links. So the update algorithm for center loss is pretty simple. In each batch, we will have some SGD algorithm update. So as you see here, we'll update the weight parameter using SGD algorithm. Also, we'll update the center features in each batch. So if you see this algorithm, you only focus on setting the hyperparameter lambda, alpha, and the learning rate. So how do we train when we want to train a good model, we want some good data set. Currently, for the face, the LFW dataset is too small, so if you train on this dataset, you cannot generalize real on some unseen face images. So that's why we choose another large dataset called CISA web face dataset. It is probably the largest dataset available to us. And to get this dataset, you have to send email to the original authors and sign some paperworks. Then you can get a private download link. In our project, we also do some survey about the current face dataset. As you see here, CISA web face is indeed the largest public dataset, and that's why we choose it. We have another large dataset called celebrity faces, but it's a private dataset. We cannot get this dataset. And in our method, we evaluate our method on the LFW dataset, since it's a standard benchmark dataset. And before we train our model, we have to, for the images, we have to do some pre-processing. We do not want using the original images because the faces of the original image is not centralized, so we have to do some alignment first. So as you see here, the blue box is the alignment aligned result. So in the training stage, we will use this crop out the images as our training data. And when we do the testing, we also, for each test image, we also do some alignment. Then using alignment image as the input, as the testing data. And when we design the model, we also refer some popular framework called ResNet. So it's a popular image classification model, appeared recently and win the best paper in CVPR. And the central ideas for ResNet is simple and elegant. It's the scape connection, which allows the convolutional layers of the residual block to predict residual that is add to the block's input tensors. So we train this model. We have modified ResNet as our best model to train our model. And also, after we implement our algorithm, we want some visualization method to verify the effectiveness of the certain nodes. That's why we do in this experiment. We replace the last FC layers with the two hidden units FC layers, so that we can visualize our extracted feature in 2D space. As you see here, training the model with stop loss plus center loss can certainly have a better result. The intra-class distance is more compact. This is the result of our method. As you see here, we get some comparable performance with some other state-of-art methods, and I think we duplicate the Sentinel's work. So to summarize, in this project, we have implemented the popular Sentinel's algorithm in a popular deep learning framework, PyTorch, and also we conducted some experiments to illustrate its effectively. Now I'll show how to run our models. So our model is trained on the Theta X GPUs. So this command is for training. You have to wait for some time. So this is all of our code. Basically, we have several files. One is for processing the data. So I write a data loader for processing the data. And also we have a face model. This model is actually modify the REST 18 model. And the main part is for the main code for the recognition model, and the trainer is control how to update and how to train and validate our model, and the vision part is to for some visualization. As you see here, this is training prediction, and this is testing accuracy for each approach. The training takes a long time, so I think it's not possible to show in this presentation. And this one is for visualize our method. So because for the face recognition, they have more than 5,000 classes. So we simplify these experiments and visualize our model in MNIST experiment, because MNIST only have 10 classes, so it's easy, or it's straightforward to visualize in 2D space. As you see here, this is our visualization result. So, and my code is actually can be found in this part. All my code can be found in this project. That's all. Thank you.